You and I live on a planet, Earth, orbiting a star, our sun. You probably already knew that. But our whole solar system itself is also in orbit around a supermassive black hole in the center of the Milky Way galaxy. This black hole has a name. It's Sagittarius A star, written as a capital A with an asterisk. We'll tell you why later. And just this year, on May 12, 2022, a team of scientists made a special announcement. They had, for the very first time, captured a picture of this black hole at the center of the Milky Way. Aside from just being an impressive feat of international collaboration, this picture of the black hole can teach us tons about our own galaxy and about the fundamental laws of gravity and space-time. In today's episode of our show, a special 50th episode, we'll go through how this incredible picture was taken and what it may teach us about the laws of physics.
This episode of Why This Universe is supported by Wondrium. Wondrium is a mind-blowing subscription service that offers thousands of video and audio courses on a huge range of topics. I've been a big fan and a regular consumer of Wondrium's content for the past 15 years or so, and over that time I've listened to dozens of their courses, including ones on history, philosophy, literature, math, and science. For me, it's kind of like taking an intro-level university course from a great professor on a subject you've always wanted to know more about, but without the big tuition fee and all in the comfort of your own home or daily commute. I recently started listening to a series in Wondrium on the topic of African American history. Over 12 lectures, this course explores this important piece of American history from the end of slavery through the era of Jim Crow. So if you want to learn some more about African American history or just about anything else, give Wondrium a try. You can sign up for Wondrium now through our special URL to get a month of unlimited access for free. Just go to wondrium.com/universe. That's wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper.
One thing that's so incredible about this picture of our galaxy's supermassive black hole is the fact that not so long ago, we had no idea if black holes could really exist at all. In 1915, Einstein gave us this new theory of gravity called general relativity, which describes how gravity is really the effect of space-time curving around massive objects. That same year, astronomer and mathematician Carl Schwarzschild was playing around with Einstein's equations and asked a particular question. He wondered how space-time would curve if you created an extremely compact object, something with a lot of mass squeezed into a very small space. When he worked through the calculation, he found that Einstein's equations said that this compact object would be surrounded by space-time that is infinitely curved. This is the black hole solution. But there was no real reason to believe that this object could actually exist. After all, maybe Einstein's equations would just break down at that level, or maybe nature would never produce such a compact thing to begin with. So let's tell the story of how we got from not knowing if black holes can exist to taking a real-life photograph of one.
In the 1960s, there was this period of time that we call the Golden Age of Relativity, where like a lot of very smart people were like pushing the theoretical calculations involved in relativity. And some people around that time started to think more about these black holes and started to take them more seriously, not just as a theoretical possibility, but as something that probably really existed out there in the universe. In particular, this British mathematician and physicist Roger Penrose used equations of general relativity to show that if you had a big enough star, when it collapsed, it would basically be guaranteed to form a black hole. And like, I think it was a controversial idea at the time, but they were right. And it turns out that if you have a big star and it runs out of nuclear fuel, when it collapses under its own gravity, it makes black holes. There are lots of these out there in the universe. So observational evidence of these kinds of black holes started to appear in the 1970s. So the first black hole that was identified by astronomers was in a system called Cygnus X1, This black hole is about 15 times more massive than the sun. And it turns out that it's gravitationally bound to another star, a big blue supergiant star. The gas from that blue supergiant is slowly being pulled from that star onto the black hole, forming what we call an accretion disk of matter. And that hot gas is like being spiraled around the black hole, getting heated up, and it gives off a lot of bright flashes of X-rays, which is the thing we actually see with our telescopes. And it's by studying those X-ray flashes that we can tell that that black hole is there.
Black holes, by definition, you can't just point your telescope and see one because they're black. They don't emit any light. They don't reflect any light. All the light gets absorbed that ever hits it. So like if you see the signature that's like this crazy disk of gas that's spinning out of control and like these weird flashes of light, then we can infer that there's actually a black hole there.
Yeah, and by studying how short those flashes of light are, you can deduce how big this object is. And it turns out that it's the size of a 15 solar mass black hole. So you can actually work out from that indirect light, in this case, X-ray light, that you're really looking at something that is just like what Carl Schwarzschild wrote about back in 1915. So it's been decades since these first observations of black holes. And since then, we've discovered many others. And most of them are in the kind of range of masses of like 10 or 20 or 30 solar masses. And we think of these as small black holes. I mean, they're pretty massive objects, but in the grand scheme of things, this is a pretty small range of black hole mass. But we also have concluded over that time that most galaxies, maybe all galaxies, have at their core, at their center, a supermassive black hole, like something in the range of millions or maybe billions of solar masses.
And Sagittarius A star, that black hole at the center of our very own Milky Way, is just that, a supermassive black hole, roughly 4 million times the mass of our sun. If you're hearing this maybe for the first time, maybe not, you might have this question, okay, so in the center of our galaxy that we live in is this supermassive black hole, millions of times the mass of our sun, and, we're kind of taught to think the black holes are, or in pop culture, they kind of suck everything in, right? There's these huge monsters of destruction. Why are we not concerned about, like, falling into our black hole?
The thing about gravity is like a black hole with 4 million solar masses of mass is not going to pull you toward it any stronger than some other ordinary object with 4 million solar masses of mass. So for the same reason that the Earth is going to sit on its orbit around the sun and basically not change from that orbit for a very, very, very long time, you can have stars that are moving in orbits around the supermassive black hole at the center of the Milky Way, and they can be unstable orbits that just persist for a very long time. Now, there are some things that will fall into a black hole, but they have to do this through some sort of friction. So if, you've got a cloud of gas and those little particles of gas, those atoms in the gas are bouncing off of each other, that will slow them down and cause them to kind of spiral into the black hole. That can definitely happen. But, if you were living on some star, 100 parsecs from the supermassive black hole or 300 light years from the supermassive black hole, you don't have to worry about being sucked into that black hole anytime soon.
Yeah, it's a comforting thought. I like that it's just like we're not scared about getting sucked into the sun, even though it's exerting gravity on us, right? We're in a pretty good orbit.
Hopefully this conversation doesn't cause anyone anxiety about worrying about being sucked into the sun all of a sudden. Now, that's not our intent.
No, you don't have to worry about that.
Definitely not.
So now you've been introduced to Sagittarius A star. So where does that weird star come from in its name?
Every time I hear this story, I kind of giggle and feel embarrassed for our field because it's so stupid and punny. But in certain kinds of atomic physics, excited states are denoted by a star. And I forget who did this, but when they named Sagittarius A star, he just thought it was exciting, this source, like literally.
Gotcha. So it was like an intentional pun.
It was an intentional pun. And it's kind of cringeworthy, but cute at the same time.
It's kind of cute, yeah.
So until recently, we only had, pretty good but indirect evidence of the black hole that we call Sagittarius A star. In particular, we could tell that there was something like a black hole there by measuring the stars around it, who are going in very close, tight orbits around this black hole. And by studying the way that these stars moved over time, we could figure out that, well, whatever it was, Sagittarius A star was very heavy and pretty compact. In particular, it suggests that it's about 4.1 million solar masses, or 4.1 million times as massive as the sun. And we couldn't really say how big the thing is, but it's no larger than about 45 astronomical units. So that's 45 times the distance between the Earth and the sun. So that might sound kind of big, but for something more than 4 million solar masses in mass, that's actually pretty small. So this is not ordinary matter. This is something exotic, squeezed, giant, supermassive exotic things squeezed into a relatively small volume of space.
At this point, we had lots of reasons to expect Sagittarius A star is a black hole, but we couldn't actually be sure. All we knew for sure was that there's a lot of mass in the compact space in the center of the galaxy. But for all we knew, it could have been some other form of exotic mass or super heavy plasma or something. It may have been unlikely, but a few papers have been written on some alternate hypotheses for what could explain this mass. So you never really know, unless you can snap a picture. So you want to take a picture of a black hole, an object that is tens of thousands of light years away and doesn't emit or reflect any light. And in order to know that what you're looking at is really a black hole, you need your picture to have good enough resolution at that distance so that you can make out the event horizon.
In other words, we wanted to see that this thing really has an edge, event horizon, where the equations of general relativity say it should. If we could see this event horizon, and it were where the equations of general relativity say the event horizon should be, we could be basically completely sure that Sagittarius A star is in fact a black hole.
Okay, so what did physicists think that this event horizon would look like, right? Because we were saying it's not like light can pass through, or it's not like it emits light or reflects light, right? So what were we expecting to see at the event horizon?
So if we use the equations of GR, we can kind of predict what we think a really high resolution image of Sagittarius A star would look like. Basically, these equations say that a black hole like this should be surrounded by a dark silhouette-like region caused by the extreme distortion of gravity in that region. So again, the photons you're detecting aren't coming from the black hole, but the shape of where the photons from other stuff, the picture of those photons gets distorted by the extreme curvature of space right around the event horizon. So if there was nothing in nature but the black hole, you wouldn't see anything. But there's a bunch of other stuff out there giving off light, and the shape of that light gets deformed by the presence of the black hole.
So we'd see this really deformed, strange light that is coming from the location of the event horizon. But really it's light from either things behind the black hole or farther away that's just kind of getting distorted as it travels by. But that's what we would actually see.
That's exactly right. What astronomers need to get a really high resolution image like this is a telescope with kind of superhuman resolution, really spectacular angular resolution.
I feel like most telescopes have superhuman resolution now.
Yeah, okay. I need a better word. We need some remarkably good resolution telescope. Okay, we'll go with that. I need a better expletive here. This adjective isn't doing enough work. We need a really damn good, really damn high resolution telescope. Can we say that on Why This Universe? Can I say damn?
Yeah, of course.
All right.
We can say whatever we want. So physicists needed a telescope with damn good resolution. Because light is a wave, it can diffract and spread out around things in its way. So if a telescope's aperture is too small compared to the wavelength of that observed light, that diffraction is going to worsen your resolution. It'll give you a blurrier picture, in other words. That means that for a certain wavelength of observed light, a larger aperture will let you resolve a more detailed image.
So as an example, consider the human eye. For light in the wavelength range that our eyes detect, and taking our telescopes, our aperture to be 5 millimeters, the size of our pupil, it turns out that this criterion says we should be able to resolve things as small as 25 arc seconds. Okay, so you might not be familiar with arc seconds. An arc second is 1/3600 of a degree. And to put this into context, we're looking at observing something the size of a soccer ball that's, like something like a mile away. Okay, so that's roughly what you can resolve with your human eye. You can, at that distance, you can look at something the size of a soccer ball and tell that it's a finite object. It has finite extent. It's not a point.
So this is for people with 20/20 vision, I'm assuming.
Well, so that's actually that's better than 20/20. So 25 arc seconds is like the theoretical best. Real humans have about 60 arc second resolution, so 2 or 3 times worse. And that will allow you to see the soccer ball at like 750 meters. So if you're feeling bad about your vision because you can't resolve the soccer ball at a mile, that's okay. But you probably can if you have 20/20 vision at 750 meters or something. As another example, let's consider one of our best telescopes, like the Hubble Space Telescope or the JWST. Hubble has a 2.4 meter diameter lens, and it mostly detects visible light, kind of like our eye does. So it should be about 1,000 times better at resolving small objects than the human eye is, and that's about right. And JWST is similar. It has an even bigger lens and sees mostly infrared light, so it turns out to be about the same. But again, this is about 1,000 times better resolution than the human eye. And that might sound pretty good. That's pretty impressive. 1,000 is a big number. But now let's think about what kind of resolution you'd need to see the event horizon and resolve Sagittarius A star. So taking the diameter of this black hole's event horizon and considering the distance between us and it, which is about 27,000 light years, it means that the angular size of this thing should be about 0.00005 arc seconds. That's really, really tiny, okay? This is about equivalent to trying to see an orange sitting on the surface of the moon. So, you thought that soccer ball was hard to see a mile away. This is a lot harder.
So to resolve the event horizon of Sagittarius A star, we'd need a telescope that's something like 1,000 times better in resolution than today's most powerful telescopes. That would mean a telescope roughly the size of the entire Earth. So how did astronomers do it? We'll tell you, but first, a quick break to thank a special sponsor who made today's episode possible. If you're anything like me, thinking about the climate crisis can be extremely anxiety-inducing. I try my best to live sustainably, I avoid fast fashion, and I limit my meat consumption, but it's ultimately hard to feel like I'm really making a difference as an individual. That's why, today on our show, we are very excited to be partnering with Wren. Wren is a website that helps you make a difference when it comes to climate change. With Wren, you can calculate your unique carbon footprint based on your lifestyle, and then meaningfully offset it by funding projects that plant trees, protect rainforests, and remove carbon dioxide from the atmosphere. Wren makes it easy to start taking action about climate change. By answering just a few questions about your lifestyle, you can find out your carbon footprint and what you can do to reduce it. While no one can reduce their carbon footprint completely to zero, Wren helps you offset what you have left by offering monthly subscriptions that fund projects that restore the environment. When you subscribe to Wren, you receive monthly updates from the tree planting, rainforest protection, and carbon removal projects that you're supporting. You get to see the trees that you planted, so you can know exactly what your money is being spent on. And if you sign up with our link at wren.co/universe, Wren will plant 10 extra trees in your name. That's WREN.co/universe. It will take a lot to end the climate crisis, but you can start helping today by learning more on ren.co/universe. Welcome back. So far, we've realized that in order to capture a picture of Sagittarius A star, we'd need a telescope roughly 1,000 times bigger than our most powerful telescopes like Hubble and JWST. But building a giant 8,000-mile wide telescope is just not a feasible task. So instead, astronomers had to get clever and really collaborative.
So what astronomers have done to try to accomplish this is they've taken not just one telescope, but a whole collection of telescopes in different places in the Earth, and they've used them collectively as something we call an interferometer, allowing them to act as one big telescope with an aperture size roughly equal to the diameter of the Earth. What exactly is an interferometer? Like you may have heard this word before, maybe not. And it's kind of a technical thing, like it's something you learn in an optics class. But basically, it's a device that takes advantage of the interference between different light waves to make very precise measurements. One of the early applications of an interferometer was the first measurement of the speed of light, or first precise one anyway, back in 1887 by Albert Michelson and Edward Morley. They used an interferometer to do this. Modern astronomers use interferometers for all kinds of things. When I was an undergrad, I actually built an interferometer on a tabletop experiment and brought it to an observatory and tried to detect a very specific wavelength of ultraviolet light. It was 372.7 nanometers. I still remember that number.
Yeah, like etched
burned into my
forever.
memory. Yes, 3727 angstroms. I'll never forget it. The interferometer I built didn't work particularly well, but that was my fault, not a problem with interferometers at large. So by taking this global network of radio telescopes or radio dishes, they can all kind of function together as a big interferometer and have just remarkably good angular resolution. So there's a bunch of telescopes in this network. Some of them include the submillimeter telescope, the Atacama Pathfinder experiment, the IRAM 30-meter telescope, the James Clerk Maxwell telescope, the large millimeter telescope, the submillimeter array, the Atacama large millimeter and submillimeter array, the South Pole telescope, the Greenland telescope, and the Kitt Peak 12-meter telescope. So a bunch of these telescopes all over the world, all working in unison, all combining their data at the same time to produce the highest resolution image of whatever they are pointing at.
So by using these different telescopes around the globe in unison as an interferometer, astronomers can achieve the resolution as if they had one giant telescope that spanned the entire Earth. When taken together, these telescopes are known as the Event Horizon Telescope.
If we take the typical wavelength that these radio telescopes are using, that's right around a millimeter, then it turns out that this collection of telescopes should be able to resolve objects that are as small as 2.5 times 10 to the minus 5 arc seconds. That's incredible, and it's just barely good enough to resolve something the size of Sagittarius A star.
So with this technology in place, the Event Horizon Telescope was able to take a picture of Sagittarius A star. You can see it in our album artwork right now. But we should mention that it actually took a picture of a different black hole first, one called M87. You may even remember that first black hole picture going around the internet when it was taken in 2019.
M87 is located at the center of an elliptical galaxy called Virgo A, and it's about 2,000 times farther away from us than Sagittarius A star. So you might think that this would just be way harder to see. It'd be 2,000 times smaller in angle, and forget about it. But it's also about 1,500 times bigger in mass than Sagittarius A star is, which means its event horizon is 1,500 times bigger, and it turns out these two things kind of cancel. So despite being way farther away, M87's black hole should be about as big in terms of angle as Sagittarius A star is. 3 years after seeing their first image of M87, on May 12th of 2022 this year, the scientists operating the Event Horizon Telescope Array announced that they produced the first image of Sagittarius A star. For the first time, we've finally seen this monster that's been living in the center of our Milky Way.
It's our own monster. It's like
our own monster. It's it's our own household pet, basically.
Yeah, basically.
So you're probably wondering, what do these images actually look like? We're talking about these images of these black holes this whole time. We really haven't said anything about it. And basically what you'll see is kind of a fuzzy ring of light with a black spot at the center. Okay, that's kind of what we're calling the image. It kind of looks like a big fuzzy bright donut. Okay, basically what's going on here is that the black holes produce a kind of dark silhouette-like region caused by the extreme effects of the black hole's gravity. The idea here is that the light rays will be strongly deflected or bent when they're close to a black hole. And maybe some of the light will even be captured, so it doesn't reach us at all. And the detailed size and shape of the silhouette we can predict using the equations of general relativity. And the best of our ability to measure, these images look like what general relativity leads us to have expected. So this seems to look like what astronomers and relativists expected black holes to look like when we finally produced images of them.
But remember, this is not just a pretty picture. Taking these high-resolution images of black holes lets us better measure their properties. And in the process, it teaches us a lot about these amazing objects.
For example, M87 is a spinning black hole. It's rotating on its axis. This makes it something we'd call a Kerr black hole, Kerr black hole. The images for the Event Horizon Telescope have also been used to like measure exactly how fast it's rotating, and we've learned more about it from these images. And this image has also allowed scientists to more precisely determine the mass and diameter of this black hole. We now know that its mass is somewhere in the range of 5.8 to 7.2 billion solar masses. That's billion with a B. And its diameter is right around 4 times 10 to the 10 kilometers. That's something like 270 astronomical units, if you prefer to think in those terms. Another of the scientific goals of the Event Horizon Telescope is to better understand the process of how matter is accreted onto a black hole, onto supermassive black holes. So the idea here is that matter can stay in orbit around a black hole, but friction between atoms can cause gas to kind of fall in and get closer to a black hole where it gets heated to really high temperatures. And that really hot gas can actually be really bright. In some cases, that bright light from that hot gas can be even brighter than the whole galaxy surrounding one of these black holes. M87 is actually a really bright gamma ray source, an X-ray source, because of that accretion onto the black hole. In contrast, Sagittarius A star is pretty dormant. It's kind of bright. It's, we can detect the light from it, but it's pretty dull compared to some of the other black holes. In some cases, the accretion of matter onto a black hole can power these things we call relativistic jets. These are basically beams of plasma moving away from the black hole at something close to the speed of light. M87 has jets that extend about 250,000 light years in either direction away from the black hole. The measurements of M87 by the Event Horizon Telescope show evidence of these jets, and they tell us things about their geometry close to the black hole and how much energy they carry away, things like that. And perhaps, like from a fundamental level, the most interesting thing is that this telescope also provides us with a new way of testing the laws that Einstein laid out in his theory of general relativity, in particular under these conditions of extreme gravity. So we've tested general relativity in planetary orbits and lots of other ways, and like these test certain aspects of general relativity. But if we want to understand what general relativity does or what nature does where space-time curvature is super, super big and strong, there's nothing better than the edge of a black hole to make that sort of measurement. And what we learn from the Event Horizon Telescope and these observations is that everything looks just like Einstein predicted. General relativity is held up to scrutiny yet once again. So
yeah, it's always the headline. Einstein's right again.
Einstein's right again. It gets tedious to hear that because it's so often true. But in the ledger, Einstein scores one more point.
Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.